Hello and welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmaz and today I will go over to model one of the tutorials in Diana website. The title is Bending Test on a Fiber Reinforced Concrete Notch beam. Let me describe the problem and after that I will jump to Diana environment to start modeling. In this video, I want to demonstrate how to model steel fiber reinforced concrete elements in Diana. From this point forward, I use the SFRC instead of the steel fiber reinforced concrete. The example is based on the three-point bending test of the notched concrete beam, which is follow the EN standard. This test setup is commonly used to determine the tensile behavior of the SFRC. The key parameters like the residual fractional tensile strain are obtained from the load versus crack map opening displacement or the load versus deflection curve which is generated during the test. As you can see on the screen, you can see the geometry of the test. The beam has a total length of the 550 millimeter, including 25 millimeter extension beyond each support. Its cross section is represented on the screen, and a 25 millimeter deep notch is placed at the center of the bottom face to guide crack formation during the test. To model the steel fiber reinforced concrete in Diana, I need a mechanical parameter obtained from the lab test. The main test which is used in the three-point which is used is the three-point bending test, which give us the load versus crack mouth opening displacement, as you can see in the figure 3. From this curve, we can calculate the residual flexural tensile strain, and the formula is presented on the screen, as you can see. These values help us classify the SFRC into serviceability and the ultimate condition. The class of SFRC indicates both the strength level and toughness of the material. Based on the classification, the stress versus crack mouth opening displacement curve can be defined using the guideline from the FIB Model Code 2010, as you can see in the figure 4. Now I want to describe the material properties and the modeling approach in this video. In this example, I use a steel fiber reinforced concrete class 3C based on the plain concrete of the class C30. Class 3C means the residual flexural strength FR1 lies between the 3 and the 4 Newton per square millimeter, and the residual strength ratios satisfy between the 0.9 and the 1.1. On the tensile stress versus crack mouth opening displacement curve in the figure 4, the point B represents the peak tensile strength based on the characteristic tensile strength of the FSCT of plain concrete. Point A is set at 0.9 multiple to FSCT, representing the start of the cracking. The post-peak behavior is modeled using the linear softening curve, which is defined by the 2 points. FFTS residual strength in the serviceability limit state and FFTU residual strength in the ultimate limit state, which defines the slope between the point D and E in the figure 4. The point C, where the SFRC curve drop after the peak, is founded by intersecting the softening branch of the plain concrete curve using the Hordijk model and the extrapolated line connecting the point D and E. As you can see on the screen, we have a material properties for this simulation. It's a two-dimensional representation of the beam, and with a quadratic mesh and linear elastic material are used for the concrete, steel, and the interface. For the SFRC behavior, I applied the FIB model code for defining the tensile curve, and the nonlinear analysis used to capture the complete load differential response. And at the end, the tensile stress versus crack map opening displacement curve from Diana is compared with the FIB model code result. Now I want to jump to Diana environment to start the simulation. So this is a Diana environment. I'm using the Python script to create the geometry of the model. So for this purpose, I only need to copy and paste the Python script to the command console and wait for a second until Diana creates the project and the geometry. Very good. Now let's see what we have in Diana by the Python script. In the project setting, we have a structural analysis module. For the measure type, I use the hexahedron or quadrilateral measure type, and for the meshing order, I use the quadratic meshing order. With the for the mid-cycle location, I select the linear interpolation for this model. Also, in the I come to the unit, and we have a uniter for the length and tone for the mass. Very good. Now it's time to assign the shape properties to the model. In the geometry, we have a concrete block, support left and support right. To assign the material properties to the model, I want to start with a concrete object. In the element class, I select a regular plane stress, and for the model material, I need to define the new material. I call it concrete underline FRC. In the case of the concrete and masonry, I select the total strength base crack model. I need to input the data for the linear material properties. The first one is the Young modulus 33550.6. For the Poisson ratio 0.15, and for the mass density 2.4 E minus 9. For the total strain base crack model, for the crack orientation, I select the rotating, and for the tensile behavior, I want to select the FIB fiber reinforced concrete. We have a different the options in the crack map opening or a strain curve stress input. The first choice that I want to use is the stress versus the crack map opening displacement, and I need to input data for the different aspect of this model. For the uniaxial tensile strength, for the uniaxial residual strength, sigma I 2.03. For the crack map opening, 0.00225. For the uniaxial residual strength, sigma j 1.49. And for the crack map opening at a sigma j 0.025. And uniaxial residual strength, sigma k 0.75. Crack map opening 2.5 millimeter, and ultimate crack map opening 8 millimeter. For the crack bandwidth specification, I select the G. And for the reduction model, I want to select the damage base. And for the compressive behavior, I want to select the parabolic. And after that, I have to input data for the parabolic compressive curve, compressive strength 13 Newton per square millimeter. compressive fracture energy 35.1256. For the residual compressive strength 0. For the reduction model, I used the Vehico and Collins 1993, and the lower bound reduction curve is 0.4. And for the stress confinement, I selected no increase. Very good. And for the geometry, I need to define the new geometry. For the concrete object, I call it thick. And the thickness of the concrete is 150 millimeter. And the local axis for the direct input is a 1, 0. Very good. Now I'll come to apply and close. Let me show you what we have in the material properties. We have a concrete, fiber reinforced concrete, and as an alternative to the tensile curve based on the crack map opening displacement, we can use an input based on the model code 2010. For this purpose, I duplicate the material properties and change the name to the model code. And for this purpose, I need to change the crack map opening definition. I select the model code 2010. And these both approach generate the same tensile curve. Very good. Now I close the material properties. We also need to define a linear elastic material for the support left and right, and also a loading block. So I come to the shape properties and select the block, support left and support right. For the element class, I select the regular plane stress. For the material, I need to define the new material properties. I call it steel in the class of the steel. For the material model, I select the linear elastic isotropic material model, and I need to define the Young modulus 2E5, 0 for the Poisson ratio, and also 0 for the mass density for this object. And for the geometry, I select the thick, same as the previous step. Very good. Now we have assigned the all material properties to the geometry shapes. After definition of the material properties to the all geometry shape, now I want to assign the interface between the loading block and the support left and right. For this papers, I come to the interface. I call it interface. The connection type also is interface, and the mode is a close. For the source type, I select the edge. And for this purpose, I hide the concrete and select the bottom edge of the loading block and the upper edge of the support in the left and right. Very good. And for the target, I also select the edge, but now I hide the block. Let me clean the target box and show the concrete. And for this purpose, I need to select the edge of the concrete, which have a connection with the loading block, support left and support right. Very good. For the element class, I select the structural line interface, and for the material, I need to define the minimum material properties. I'll call it interface. And for the class is a linear interface element, and for the material model is a linear elastic material model, and for the type is a 2D line interface. With the normal stiffness in the y direction, I input the 1000, and in the x direction, I input 10. Very good. And for the geometry also I need to define a new geometry for that. The shape type is a line, element class is a 2D line interface element, and the thickness is a 115 millimeters. Very good. Now I come to create, and now I have a all interface in the model. In this step, I want to define the support to the model. So I come to the support. I call it first one is a support left. I need to create a support set. And the target is a vertex. And I select the one vertex, middle vertex of the left support. And I need to fix the translation into T2. The next support that I want to define in the model is a support right. I need to create a new support set. And the target type is a vertex. And I select the middle vertex of the right support and select the fix the T1 and T2. Very good. And the last one is related to the loading block. The vertical load is applied in this model is in a prescribed deformation type. So we need to attach a support in the y direction to the top edge of the loading block. For this purpose, I need to create a new support. I call it support block and define the new support set. The target type is a edge. I select the upper edge of the loading block, and after that I fix the T2 in this support. Great. After definition of the support, now I want to assign load to the model. So I come to the load. I call it vertical. Then I need to define the load case. I call it vertical 2. The target type is an edge, and the load type is a prescribed deformation. I select the upper edge of the loading block. The degree of the freedom type is the translation. For the support, I select the support block. And for the prescribed deformation, I put the -1 in a y direction. Come to create. Very good. Now we have a support and load in this model. Now we are one step behind the analysis setup. We need to create and generate mesh in this model. So I come to the mesh properties. For the target, I select the shape. And I select all geometry object in this model. And for the seeding method, I select the element side. For the element side, I input the 15 millimeter. I come to apply. But I need to have a more finer mesh around the notched area. So I select the edge in the target type. And for the seeding method, I select the element size. And now I select the two edge of the round notch area. And the dimension and the desired size is a 4 millimeter. Very good. Now I come to close, and after that, generate mesh. So we have a generated view, mesh generated view of the model. The last step is defining the analysis setup. And for this purpose, I prepared a file in advance to show you what we have in the analysis setup. And after that, we will review the results together. Let me explain what we have in the analysis part, and after that, we will review the result. In the analysis set, I use the structural nonlinear analysis, and for the execute block, I use the load step with a different value and step. And for the equilibrium iteration, I select the Newton-Raphson method, and the convergence node that I want to satisfy is the energy and also force. In the result part, the first result that I want to show is related to the total displacement in the y direction. So the maximum value is 0.42 millimeter and the minimum is a minus 4.22 millimeter. The second result that I want to present is related to the force versus the displacement plot. So for this purpose, I come to the FBY and select the node. In the upper edge of the loading block, click right on FBY and show table. Very good. We have the vertical reaction forces for the each load step. And also, this third result that I want to show is related to the crack width. So I come to the element result, crack width, ECW. And we have a contour of the crack width in direction 1 in an integral point. In order to plot the curve of the tensile stress versus the crack map opening displacement representative of the steel fiber reinforced concrete sample, we first select a node and element in the notched area, and I want to ask it to display the crack width value for the each load step. So I come to the notch area. In the node, I select one node. This node is related to the element 1 in a notch area. So I come to the ECW1, click right, show table, and as you can see, the blue line is related to the node 5 element 1 for the ECW1 for all load steps. The next result that I want to show you is a total stress, Cauchy total stress in an integrated point. So I come to the SXX, click right, show table, and the blue line is related to the element 1, which is in the notched area, and the node 5. You can easily copy and paste data related to the node 5 element 1 to the Excel and compare the result. As you can see on the screen, in this graph, we have a comparison with the tensile stress versus crack mouth opening curve, which is provided by the FIB model code for the SFRC material and plain concrete, and also the Diana results. We have a good agreement between the result of the Diana and the FIB model code. Now I want to show you how you can find this tutorial on Diana website. So I come to Diana website. In the Get Started in the tutorial section, based on the tutorial type, analysis type, and the modules required, you can find your required tutorials. For example, here I select the structural nonlinear analysis, and the module required for this tutorial is the expert and the structural. So, yes, scroll down and you can find the bending test on a fiber reinforced concrete notched beam. Thank you for your attention. Please subscribe to Diana YouTube channel.